Right. So, what I thought I would do at the very end of the course is give you some more astrophysical examples, right? And for these two lectures, what we will be doing is I will be giving you examples from the solar corona. Two reasons. One is it's my field. I work on phenomena in the sun's outer atmosphere, which is called the corona. We've already discussed some of these things. Second, there is no better lab, so to speak. The sun and its outer atmosphere is a great lab for testing out astrophysical applications of fluid dynamics. Is an excellent lab for, I put lab in apostrophe, for astrophysical fluids and plasmas. The meaning of this statement will become a little clearer as we go along. Okay. In particular, what I'll be focusing on is we have talked about the solar wind. Remember, I mean, we have when we talked about the solar wind and accretion both in one unified way, we've already talked about this. But for the time being, what I will focus on is the phenomenon of reconnection, because we've been discussing reconnection of late, right? And how reconnection is a means of energy release, how reconnection is a way of converting excess magnetic energy into heating the plasma and in accelerating particles and so on and so forth. I will show you examples of this particular phenomena, not direct. It's not really possible to directly image reconnection, directly say this is where reconnection is happening, but to the extent possible, these are some of the best examples of the fact that reconnection has to be happening in these phenomena. Okay, examples from solar coronal physics. This is what I'll be showing you. In particular, examples such as flares, coronal mass ejections, which are often called CMEs, for coronal mass ejection, CME. Okay, so I will show you some of these examples, some very spectacular data. As we always say, pictures are worth 1,000 words, movies are worth even more. Okay, so by way of introduction, it's worth emphasizing over and over again that the sun's corona is a restless place. What is the sun's corona? Well, it's the outermost atmosphere. It's the outermost layer of the sun's atmosphere. In some sense, we on the Earth, at least up until the magnetosphere, we are also part of the sun's corona, although we are as far as 215 solar radii away from the sun. So just to give you a sense of perspective, so the sun is here, right? Say, and this would be one solar radii, say that's the sun, and the up until this is symbol for solar radius. Okay, so this would be what I've drawn here is roughly the photosphere, the observable surface of the sun, and the corona would extend up to somewhere like this. Okay, the corona would be up to about 2 to 3 to maybe as much as 10 solar radii, say, to about 10 solar radii. Okay, but we on the Earth, okay, this is the sun. We on the Earth are situated at 215 solar radii away from the sun, and this 215 solar radii, this is often called 1 astronomical unit. So this is something to be kept in mind. Okay, So, we will be focusing on stuff, on eruptions and everything happening very, very close by, somewhere here. Okay. But the effects, and the solar wind is of course blowing out, right? It's blowing out. And on top of the steady solar wind, there are also these blobs called coronal mass ejections, which are being ejected, and sometimes they reach the earth. Okay. And just to give you a sense of the distance, I mean, this is not drawn to scale, of course. I mean, this is just one solar radii, and that's why I've drawn this. We are very, very far away. Okay, we are 215 solar radii away, and our Earth's magnetosphere as such is impacted by the solar wind and also by the transient phenomena such as coronal mass ejections, which are ejected from the sun. So I just wanted to emphasize that. And and the fact that the sun's corona is not a nice placid place. It's quite restless. Lots of things keep happening. Okay, and the corona is 1,000,000 degrees hot. About million meaning about 10 raised to 6 Kelvin. And compare with this is about 6 times 10 raised to 3 Kelvin. At the photosphere, at the very base, it's only about 10 raised to 3 Kelvin, 6 times 10 raised to 3 Kelvin, almost 10 raised to 4, right? But as you go away, as you climb up in the atmosphere, you come to a place, the outermost layer of the sun, which is called the corona, which is 1,000,000 degree hot. Rather strange, you are actually moving away from the central energy source, which is at the center of the sun, the core of the sun, which is where nuclear fusion is happening, and so you're moving away from the energy source, but you're getting hotter. As such, it seems to violate the second law of thermodynamics, but not really. Okay, the first law actually. But we will find out that that's not really the case. But nonetheless, this is a very interesting, this thing called the coronal heating problem. Why is the corona being heated? How is the corona being heated? This is one of the most interesting problems in all of astrophysics, the coronal heating problem. What heats the corona to 1,000,000 degrees? This is a question we are asking. Okay. The answer is probably many small, and you got it, reconnection events. And I emphasize the word probably because we don't really know for sure. Anyhow, getting back to our narrative. Right. So now, outer atmosphere, as we know, is not static either. It's blowing outwards. It's blowing outwards to form what's called the solar wind, and we on the Earth here are immersed in the solar wind, even though we are so far away. Okay, we are immersed in the solar wind, and the solar wind exerts outward pressure. Of course, it's blowing outwards and it exerts outward pressure, and together, and it's also a magnetized wind. Although our treatment of the solar wind did not include magnetic fields. It's a fact that, and then the gross features of the solar wind can be explained even without magnetic fields, but there are some very important things that cannot be explained without magnetic fields. And it's the fact that the solar wind is magnetized. It carries magnetic fields. Okay, and so together with the magnetic field, it carves out a bubble called the heliosphere, and it extends out to the heliopause about 30 times Pluto's orbit. So taken together, this would be what's called the solar system. I mean, this thing is the outer limits. You could also roughly call this the solar system. Okay, up until the point where the solar wind keeps blowing, so to speak. So that's the other thing is the corona as such is also a rather restless place. It's susceptible to violent departures from the placid equilibrium state, and it's worth wondering why. Why is this so? Okay, the answer is not easy, but This is a fact. Okay. And examples of departures from a place at equilibrium state range from gentle waves to small energy releases to large spectacular flares that are often accompanied by ejections of of coronal mass. Okay. And so here is a place where I want to show you several nice little examples. Let me start with the gentlest things first, gentle waves, small energy releases, so that you have an idea of what's going on in the corona most of the time. Okay, pretty much all the time, one would argue, and then I will go on to illustrate some of these larger, more spectacular events. So let me play this movie, and what this is you can see this is real data, by the way. This is data taken by the Atmospheric Imaging Assembly. It's taken aboard, taken by a spacecraft, a NASA spacecraft, right? So I'll keep playing this movie because it's so spectacular and there's plenty to talk about it, right? So now you can see the solar surface kind of rotating, okay? And this is what one would call the limb of the sun. Okay, this is the edge of the sun, so to speak, and anything out above here would be what's called the atmosphere of the sun. Now, this is imaging very hot plasma, certainly a few million degrees Kelvin. Okay, so therefore, since we are imaging such hot plasma, we're definitely not imaging the photosphere, we are definitely imaging the corona. So whatever features you see here, okay, by the way, this is not taken in visible light, this is taken in extreme ultraviolet. Okay, so the features that I want you to concentrate on are these things, these little things which look like loops, right, and these bright events, okay, these bright things, right. So the main thing that you can see here is that these loops seem to be over the time scale of, I would say we are looking at a time scale of a few days, just judging by the time the number of rotations that I can see here, right. So we are really looking at a time scale of several days here, and over these several days you can see that these loops are pretty much static, but not quite so. Okay, there are departures from equilibrium, from whatever the steady state is. That's what I mean. You can clearly see that these loops are gently moving, sort of waving around as if in a breeze. Okay, so this is what I mean by departures, small scale departures from equilibrium. So this is one thing I wanted to point out. The other thing I wanted to point out, very, very important, are these brightenings. These little brightenings here. You can see that plasma is moving from here to here, and you can also see these brightenings. These are probably signatures of small scale reconnection events. These are what are called active regions. And I keep talking about these loops as if you're actually seeing the magnetic fields. Okay, that is not true. You cannot really see magnetic fields at all. But on the other hand, what you can make out is that plasma, what these are, this is actually imaging a few million Kelvin plasma. That's what it's actually imaging, isn't it? So what happens is plasma likes to flow. If there's a magnetic field, if there's a magnetic field bundle like this, plasma will like to flow along. Plasma flows along B field lines not across. You can understand this simply from, although it's really a fluid treatment, you can understand this from the fact that particles like to gyrate along. Particles do not like to cross magnetic fields, right? So when we see these spectacular images and say that these are magnetic field lines, what we are really saying is that the plasma flows, which is what we are really imaging, trace out magnetic field lines. This is what we're really saying. Okay, this is an example of gentle waves, I would say. We saw, we saw examples where, the magnetic field lines were sort of bending a little bit over the time scale of a few days, over the time scale of some, say about 30% of a rotation, maybe less than 30% of a rotation. I'm estimating this from the fact that it takes 27 days for the sun, at least at the equator, to complete one full rotation. Okay, and we also saw some examples of small energy releases. You can see that there are these brightenings, right? These are probably what these small scale energy releases are. Okay, and this is probably due to reconnection. Okay, so this was one example. This is yet another wavelength. This is in 304 angstrom, and this is not on the same day, this is on a different day. Okay, you see this little spray here. You see this little spray here and plasma coming back, right? So this is yet another example of small scale energy releases. This is not a large flare or a large energy release or anything. It's actually quite small scale. There is some brightening here. So this is a good example of what I would call a spray. The nomenclature is quite obvious. It looks like a spray. What's being sprayed outward? Well, it's plasma that's being sprayed outward. That's the answer. Okay. These are examples range from these kinds of gentle waves to large spectacular flares that are often accompanied by ejections of coronal mass, which, as we said, they are called coronal mass ejections. Okay. Now, before playing movies of flares or coronal mass ejections, it's worth discussing why the corona is so dynamic. Why are these motions always present in the solar corona, either gentle motions or sometimes violent eruptions? I've not shown examples of those yet. I will show you. Okay, why is that? Well, the dynamics in the corona are dominated by the magnetic field. The magnetic pressure dominates. In other words, the plasma beta, which is defined by the gas pressure over the magnetic pressure, this is much less than 1 in the solar corona. In other words, the magnetic pressure, the denominator, dominates. This is, what it is, right? The other thing is the overall pressure is very anisotropic. Why anisotropic? Because of magnetic fields. We know this, right? We know that the pressure tensor, once you introduce a magnetic field, the isotropy of the pressure tensor is broken, right? In other words, the pressure is very different along the magnetic field as opposed to across the magnetic field. And also, we have seen this, we discussed this at length. The presence of a magnetic field means that there are several new characteristic modes. Sound waves, yeah, but other kinds of modes such as the alphane mode, alphane, slow and fast magnetosonic modes. Right? So this is what I mean by saying they are like sound waves, but rather somewhat modified. And these modes can jiggle the plasma around. Okay, and much of the movements that we are seeing are probably manifestations of some of these waves. We are probably directly observing, maybe not pure waves, maybe a combination. Okay, maybe not pure modes, but a combination of modes. But most likely what we are observing is a manifestation of these waves. So you see, I mean, all this discussion we had about waves and dispersion relations and everything, they were not simply dry academic discussions. Here you go, I mean, here are concrete examples, and people spent a lot of time in analyzing, say, the time period, the observed time period of these waves, trying to figure out what the physical conditions are in the plasma, what the temperature is, what the pressure is, what the magnetic field is, and so on and so forth. And then going back and trying to see if the wave period or if the oscillation periods that are observed there correspond, can in some way be linked to these waves, and therefore we can understand the nature of these oscillations. So people, spend a fair amount of time interpreting these beautiful observations. Okay. Now the other important thing is that the magnetic field configurations are often stressed over and above their potential states. Why? I'll tell you in a minute. And once that happens, the magnetic field lines have a habit of rearranging or reconfiguring themselves via a process called reconnection, which we have discussed, of course. Okay, and this process of reconnection enables these stressed magnetic field lines to return to a lower energy state, releasing excess energy in the process, and this excess energy goes into heating the plasma. That's the origin of these brightenings, and also accelerating particles, and sometimes enabling entire blobs of plasma to be flung out. Okay, let us talk a little bit about this point. Okay, because it's not exactly evident how this is. Let me give you, at least on the sun, an example where this could, how exactly this could happen. Okay, so you see, we know that the sun rotates faster at the equator than at the poles. This is called differential rotation. Okay, so this arrow shows you, faster movement, and we've already discussed this when we were discussing the frozen end condition, and when we were discussing some ideas about the solar dynamo, about the way magnetic fields are generated. But here is another way of looking at it. So now imagine a magnetic field whose foot points, one is here, a magnetic loop, which is like this. One foot point is anchored here and one foot point is anchored here. You can immediately see that this foot point is dragged faster compared to what? Compared to this foot point. Okay, so this loop, what will happen is this loop gets tangled up, right, because this foot point moves faster than the other foot point. So this loop does not does not retain its configuration. It tends to get twisted. Okay, of course loops cannot cross like this. This is just in 2 dimensions. In 3 dimensions they don't have to cross. But the point is, it's much like a telephone cord. Okay, in old fashioned landline telephones, you have the cord connecting the handset to the receiver. So that telephone cord, it often gets twisted. You must have noticed it's somewhat like that. Okay, so what happens is this loop, the loop gets twisted. Gets twisted. Okay, when it gets twisted, it's stressed. You can think of this as the lowest energy configuration, the potential configuration, given boundary conditions here and there, given that maybe this is the positive pole, north pole and south pole. That's a boundary condition. Okay, and you solve del square phi equals 0 to find out the potential field configuration. It would look something like this. Okay, now because of this differential rotation, okay, and this differential rotation happens all throughout. I've just exaggerated this just to show you. I've just exaggerated the scale. Okay, it's not like a loop needs one foot point needs to be anchored near the equator and one so close to the pole. No. This loop can be quite small. But nonetheless, because of differential rotation, there's a scope for this loop to get twisted. And when it gets twisted, it gets stressed. Okay, and what do I mean by stressed? Well, the magnetic field configuration now is non-potential, okay, and the amount of energy that's stored in this magnetic field configuration is over and above the lowest energy configuration. And the rest we have discussed over and over again, which is that this non-potential, this stressed or non-potential field configuration relaxes to a lower energy configuration via a process called reconnection, which is cutting and pasting of field lines, and it enables them to return to a lower energy state, releasing excess energy in the process. And we have seen some examples of this kind of energy release. Now we will discuss flares and so on and so forth in some more detail, but before leaving, let me show you at least one example. Here you go. You see this brightening here, this is what's called a flare. Okay, this brightening. Okay, this is a very small snapshot. I mean, this is a very small region of the sun blown up. This is in extreme ultraviolet 195 angstroms, and this was one of the largest flares ever recorded. Ever since we started, getting detailed images of the sun. And so, what is the flare? Well, at this particular wavelength, you see this brightening out here. That's the flare. Okay, and it's not like this that the brightening happens only at this wavelength, only at 195 angstroms. It happens all throughout the electromagnetic spectrum. So I want you to concentrate your attention on the brightening. Okay, and also these lots of, immediately after the brightening, you will notice that there are lots of little white dots. Okay, what these are, well, this brightening is simply photons, but along with the photons, okay, particles, massive particles, okay, like alpha particles or protons or even heavier particles, okay, particles with finite mass are also accelerated, okay, and these accelerated particles go and hit the detector, okay, which is observing these, and so they cause ionization streaks. And so these white dots that you see are actually ionization streaks arising from energetic particles hitting the detector. So they are indirect evidence of the fact that particles are also accelerated in this episode of large energy release. Okay, we will talk a little more about flares and also some about coronal mass ejections, which are often accompanied and many times accompanied by such flares. Okay, the commonality is that both of them represent energy release phenomena, and in both cases this energy release phenomenon is thought to be facilitated by the process of magnetic reconnection. Okay, so that's all for today. Thank you.